Hello and welcome to the new tutorial of ABAQUS. In this tutorial, we'll learn about the c-phi reduction method of slope stability, which is generally adopted for any finite element software like ABAQUS and Plexus and even in ANSYS. So this is the sample model which we are going to create in this tutorial. You can see this is a kind of a 2D, 3D slope. So we'll create a 3D slope again. I have already created a tutorial on this. So I will redo the series on the slope stability with a 3D slope, and later on I will convert this 3D into a 2D slope in the next video. So this is the basic slope. We'll create our properties based on general Moore column properties with some permeability, because we are going to be using the slope stability reduction factor with soil step, which is the Bayes equation based integration procedure. So let's go and create a model. We'll name it as CPR because that's a c-phi reduction model, and click on OK. We'll start with the part. We'll create a geometry. So it is a 3D solid geometry with a size of about 100 meter. So this is the general size of the geometry which I am going to create. First we'll create a 30 by 30 toe. So let's just dimension it 30, and height will be 30. So this is the general dimension of 30 by 30. Then we have the dimension of 30 by 30, then 55 by 30. It's basically not 55 by 30, but we'll create a 55 by 30 box anyway. It will be 55, and then it will be 30 here, and the overall gap between the this 30 bars are 15 meter. So we'll create one line of let's say, or maybe a box of 15 meter by 30 meter. So this is a box of 15 meter by again a 30 meter. So that's 30 already. So now we are going to be moving this geometries together. Click on done. Okay, all of it done. Move it here, and then move the upper part or this part done to here. Now this geometry is already moved to its location. Now we'll move all of the geometry in the grid, so that whenever we are going to edit, it doesn't create any issues. Now we'll join the and create the slope. This is the slope. Now this is we'll remove the internal dimensions, which are these ones, in this. Now we'll join the bottom line, so as to not have any connections between the continuous line segments. Now I'll click on done. The depth we can keep up to about 2 meter, so we'll go with the 2 meter depth. This looks fine. And after this geometry creation, we'll go into properties and we'll create a property module which will be of soil. So this will have a general density property of about 1800 kilogram per meter cube, and the mechanical elasticity will be of let's say 30 E6, that is 30 megapascal, and Poisson's ratio we can keep up to 0.4. Then in the plasticity we can go for the Moore column plasticity. Here it is, and with the friction angle, initial friction angle we can go with 30, assuming it as a sand, and dilation angle for the friction angle generally we take 30 minus whatever the friction angle is in the positive absolute value, which is 5. So 30 minus 30, 35 minus 30 will be 5. So that's the initial friction and dilation angle. And we can use a c-phi soil because we are going for the c-phi reduction method. We'll create some cohesion value as well. However, generally sands do not have very high cohesion value, but we'll keep a value of 5000 here. Maybe keep a larger value 15,000, and absolute plastic strain will be 0. So here because the stress reduction factor is needed to be involved, before that we'll just create a permeability values. For the sand we can take about 1 e to the power minus 5 kind of permeability value and void ratio of 0.9. That's good enough, and the specific weight of the water will be 9810 kilonewton per meter cube. That is the specific weight density multiplied by the g. So 9.81 multiplied by the 1000. So in the Moore column plasticity, we'll create a field variable in both cohesion and in the frictional values. So here in the field variable module, we'll create a field variable which will be the reduction factor. Now let's move on to the table of properties where we have already calculated. Actually, I have already calculated. You can also calculate it based on the formula given in the sheet. Basically, there is your phi, which is 35 degree. Your dilation angle, I am generally taking the dilation angle 5, 4, 3, 2, 1, while the angle of friction is higher than 30 degree. For let's say it's 30.26, I am taking the dilation 1, and whenever the dilation angle or friction angle reduces below 30, I am taking the dilation equal to 0. So that's how I am dealing with the dilation angle. You can have your own law for the dilation angle, but for the phi, a specific law I am going to denote here, which is basically you have to divide the friction angle with the reduction factor. So this is the formula. You can see degrees tan inverse, which is a tan of tan of radian of 30 degrees. So 35, which is generally in degree, we convert it into radian because the Excel creates tan from the radians. So tan of 35 radian, that will be divided by C2. C2 is your this reduction factor, 1 starting from 1, because initial factor of safety is generally higher than 1, and it's going up to 2, and you can increase the higher factor of safety based on your own condition. So that way you can change it, you can reduce the cohesion. So I have initially taken the cohesion equal to 15,000, and it is going up to 75,000 Pascal, which is 15 kilopascal to 7.5 kilopascal. So these are the values which I am taking. So I am just going to copy the cohesion, and I am just going to paste it here as values only, and then this reduction factor I am just going to copy, Control C, and paste it here as values, and I am just going to copy this values and paste in this box. Yeah, so like that, and I am going to remove and cut these values, cut and paste them in the field variable. Absolute plastic strain will be 0, so you don't have to define it. It automatically takes the value of 0 for the absolute plastic strain, so no need to worry about that. Again, the field variable you can paste it as it is. It will go up to 2. The dilation angle you can reduce it accordingly, but I'm just going to copy the other values from here, and I'm going to copy them here. So here you can see till 19, and the dilation angle again I will just copy all the values, Control C and Control V. So basically dividing the values of friction and cohesion by the reduction factor, which is going from starting from 1 to 2, and this will be inserted in the problem as a field variable. So the field variable will vary, and the phi will be controlled by the field variable. So that's how we are going to solve the problem of factor safety here. So it's basic maths, and I guess you all know the theory of how c-phi reduction works. We divide the c and phi both by a factor. For phi, we divide the angle and tan of the phi by the factor, and then return the value of degrees by taking the inverse of that divided value. So that's how we create it. So this is the general procedure of creating the properties. Now I'm going to click on OK. So this is the properties we have assigned. Now we can just create a section, and this whole section can be assigned a property of a section of soil which we haven't created. We'll create it on the fly. It will be solid homogeneous section. We'll call it soil, and soil will be the material which we have created, and click on OK. So that's how we have created the property assignment. So this is the first chapter of our video, and we'll continue in the next chapter again. Now after creating the properties, and we'll just move this part to the assembly. This is already moved to the assembly. There's nothing to be done here. We'll go to step. We'll create a geostatic step first. That will be this geostatic step, because this will basically do the consolidation for us. We can go with nonlinear geometry on, and based on the incrementation you can just go with the fixed incrementation. You can go with unsymmetric matrix storage here, and click on OK and dismiss this. Again, sorry, after the geostatic we'll create a soil system. So this is a soil system which we are going to create. It will be steady transient, basically transient consolidation, and the time period will go with the 10 seconds time period. You can provide automatic installation, but I am going from none here. As an incrementation, the minimum incrementation which I have provided here is 0.001. Initial increment we can change from 0.10 to 0.1, and maximum can go up to 1. We have to provide a maximum pore water pressure change of about, let's say, 10,000, basically 10,000 10 kilopascal. You can change this value according to your own. I am going to increase the number of maximum increments so that our analysis do not fail, and change the metric storage to unsymmetric, and the default load variation over time will be linearly varying over the step time. So that's how we have defined the steps. We can also change the field output or history output request. So now I am going to go for the history output at every x unit of time, which is 1 second, or instead of 1, 0.5 second of time, because that's what I am going to go for to look into my field variable. So we have dealt with this step. There is nothing to be done in interaction. We'll directly move on to the loads. In the load module, we will apply just the gravity loading. We'll create a initial step. In step 2, we'll provide a gravity loading, which will be called gravity. Gravity, and we'll click on OK. The gravity will be working in the negative y direction, because that's how it will be working. As you can see, the negative y direction will be downward, so that's how we'll apply the gravity. Now in the boundary conditions, we'll create fixed lateral boundary condition and every other boundary condition. So in the BC module, we'll first apply fixed boundary at the bottom. So it will be applied from the initial stage, and we'll go to the bottommost and select this set as a surface and apply Encaster boundary to this. Then we'll apply roller. Now what this roller boundary condition will do is that it will allow only the vertical displacement, but not any other displacement. So this face and shift click this face. So both this face will have a roller boundary. So we want to apply, let's look into the viewport. We want to control the z direction displacement, that is u3, and we don't want to control x and y direction. So with u3 we have to automatically control ur1 and ur2, because this rotation should be controlled, and that's how we have applied the roller. Now to the other roller, I'll call it roller 2. So this boundary and this boundary will come under the roller boundary condition, where we have to stop the x direction movement. So u1 should be stopped automatically. u2 and u3 opposite rotations, 90-degree rotations, should be stopped similarly. So these are the roller boundary condition. With roller boundary condition, we have to apply the pore water pressure boundary condition at some location, because we are going to be using a soil steps. So at this surface, we are going to apply a pore water pressure 0 condition. So here the pore water pressure will dissipate. So that's our boundary conditions and loading. In the predefined field variable, we can go with geostatic stress. You can just calculate the geostatic stress based on whatever phi we have taken or created. So I'm going to go with this. I'm going to call it GS and click on continue, and if we have sets, set 1. So stress magnitude. So let's just before applying this, we'll go to assembly and move this section to this point, so that we have a definite origin with us. So now we have the origin with us. Now we can go to the load and create a predefined field condition, which was called GS, geostatic stress, to the whole part. So stress magnitude at point 1, which is this, which has a vertical coordinate of 0. The stress magnitude will be maximum, which is 55 times what was the density which we have taken, 1800. So let me just calculate it. 55 times 18. Okay. 55 times 18, that's equal to 990, 99000, but that will be compressive, so we'll change the sign to negative. The stress magnitude at the top will be 0 and the vertical coordinate of the top will be 55 and lateral coefficient will keep us 1, and that's how we'll apply the geostatic stress state. And in others we'll just create we can create pore pressure, we can create everything else, but the most required value here is the void ratio, which again we have to apply as the value which is 0.9, which we have already defined in the parameter property modules. So you can rename it as VR. Yeah, so VR and GS both are defined. Now we have to go to mesh and mesh element type. First we have to go to part and we'll go to mesh element type. Yes, and we have to go to pore fluid stress. Yeah, and again standard will be the format. We are not going for explicit integration scheme, so standard C3DP at D8P. That's how we are going to mesh it, and for the meshing we'll create a size of 1. Oh, 1 is looks too large, so we can go with a size of 2. If it's not going too large, so just click on yes. So that's the mesh which we have created. You can further refine your mesh based on some division, geometrical division. So after mesh load and everything else, we can just go to job and create a job which was already created, but I'm just going to delete this job and create a new job which will be CPR1 continue. Okay, so again the field variable which we have created needs an amplitude to be moved, so we'll create an amplitude again. This will be our CPR because we have to vary the field variable based on some amplitude, so we'll create a tabular amplitude with the input file which will automatically gets inserted into the input file. Now we have this files in the sheet 2. I have created the amplitude, so I'm just going to copy this. Okay, so just let me check, amplitude is on the other side. So yeah, so I'm just going to copy this and paste it here. So now you can see that the step size which we have selected is 10, the overall step size of soil step, and the amplitude is moving from 1 to 2 linearly in this tabular format from using this amplitude. So I'm just going to click on OK, and although I'm not going to use this amplitude right now, but I'll be using this amplitude when I change the things in the input file. So this is the part 2 of chapter 2 of the this lecture. So we have created the job file. Now in the last chapter we'll start to write the input. We'll just write the input, and after writing the input we'll go into the working directory where the input file has been created. I will open this to insert. I will attach this file, or you can just look into the YouTube tutorial and write yourself down. In both of these in Notepad++, so you can see this insert file. I have written the instruction just before the step module and in the step module before output request. So I'm just going to show you how you are going to place these file lines in the latest versions of ABAQUS, like ABAQUS 2020 and 21. I guess there is not a necessary to place this tweaks in the input file, but still most of the time this placing works. So just before the step module, we'll just copy these 2 lines initial condition to define them. Just copy them, and we'll go into this input file just before the step module. So here is the step module. We'll go here and make a space and place it here. Initial condition type field variable equal to 1. So the field variable 1 is defined here. Now the slope 1 is not the part which we have created. We have created part 1. So I'm just going to copy the upper set, copy it and place it here, like part 1 1 set 1 1. So initial value of the field variable is 1. Now the variation of field variable, we have to place it in the output request. So we're just going to copy this and place it just before the output request where we want to change the value. So in the step 2 we are going to change the output request because step 1 is the geostatic step. So before that, in output request, here is the output request, and you can just place it before here like so. But again you have to change the slope 1 set 1 to part 1 1 set 1. because that's the name of the part or the whole part set where we have applied the properties. So you have to change this set to the whole part set where we have applied the properties. So I'm just going to save it, close all of them, and I'm going to go back to ABAQUS and import the input file. Yeah, here this input file will be imported. So here is the input file. Now I'm going to go to job and create a test job for the CPR1 file and click on OK, and I'll just submit it for the run. So after the submission, we'll look into the results in the chapter 4 of this tutorial. So you can see the job has been completed, and now we'll go into the results section and into the visualization. So you can see that we'll look into the displacements directly in the U1 form. So you can see this slope is not specifically failing in this manner. However, at the toe you can see there are large displacements of the value of 0.7 millimeters. Still the slope is far away from failure. But however, from this tutorial you can learn that how you can perform the c-phi reduction method, and further if you want to plot the failure and if you want to calculate the failure, you can just plot this u1 at the unique nodal points at a specific location, let's say at this toe or at this point, and click on done here. So at this point we are going to plot the time history of unique displacement, basically the x1 or lateral displacements. So you can see with the time the displacement till time value of 0.3 are relatively smooth, and after that they starts to grow very fast. So at the point value of 0.3 you can just check out that at 0.3 the factor of safety or reduction factor is 1.3. So for this you can assume the factor of safety of 1.3. Further you can do a much finer analysis based on your own calculations, and based on this tutorial you can create the Excel sheets and the text file which you want to insert in your own input file. So I am going to finish my tutorial here. Basically the point where the displacement starts to rise drastically or your analysis basically fails is the location where you have to you actually have found the factor set. So in this case at the time value of 3 the displacements are starting to rise drastically. You can see the angle has been changed very drastically here, and at the time value of 3 the reduction factor is 1.3. So that's what I mean by 1.3 reduction factor, which is the actual factor of safety which we found for this specific slope. And you can again calculate this in the limit state softwares like GeoSlope and rock science softwares or any other software which you prefer to cross check the value against the limit state methods. So I'm going to finish my tutorial here. Thank you.